welcome back to another episode of Polly's Introduction to Computer Networks. And yeah, we do have more students popping in, and Polly did not have the time to say hi to all of you. So Bingchen, Peter, Loretta, Claudie, Mark, Vincent, Charlie, Davis, Oscar, Chen Yo, Chloe, Jared, Franklin, Doris, Cedric, Rick, Sean, and David. All of you, good morning. And you know what? We don't have other announcements today, so we'll go ahead and get into the topics. You know what? I know that some of you probably can't wait to hear exactly how TCP does RDT. All right, so here's TCP's RDT, an overview. And then I'll be introducing the finite state machine. And the very last part of the video will be to rewrite the finite state machine in another way. Okay, finite state machine is circle and arc, somewhat graphical. But I'll show you that I can actually write that finite state machine into a description. In the end, it will look like just a pseudocode that is programmable. And here, RDT of TCP. These are the characteristics. First of all, it's pipelined. So we send packets back to back in TCP as well. We could have multiple packets in one flight. And the acknowledgement is cumulative, meaning the sequence number in the ACK indicates all the packets below that up to that number are received correctly. And there's only one retransmission timer for the entire flight of packet. And so when that timer times out, then we retransmit the flight of packets. So up to this point, you will probably guess TCP's RDT looks very much like, GBN, the go back in. Now the slight difference is this. In TCP, the RDT adds a little bit something so to speed up the retransmission. And that is a special condition when the sender sees a certain number of duplicate ACKs arriving quickly. Yeah, retransmission timeout, that's not wait for that, that's quickly retransmit. Okay, so this is also called the fast retransmission mechanism. So this is something that's a little bit unlike the standard go back in, but implemented in TCP. Right. Next are the finite state machines of the TCPs. To make it simple, let's ignore the dupe ACK part, okay, the fast transmission part, and let's not talk about the other mechanisms we have not yet discussed that's implemented in TCP. If you're expecting TCP sender looks very much like go back in sender, you're correct. First transition is what? The get call from above transition. Okay, receive data from application. Okay. So in TCP sender, we generate the packet, assign the sequence number to the packet, of course also calculate the checksum, and pass that to the lower layer. So it's essentially the UDT send call. And we check whether the timer has already been started for the flight. If it does, don't do anything. Otherwise, if there's no timer currently running, we're sending a packet, then this must be the send base. Start the timer. And then we increment the next seek num. But in TCP, we are not counting packets, right? If we are counting packets, we add the sequence number by one packet. But here, we are counting the bytes. So we are adding the number of bytes in the data in the packet we're sending out. Now, you see here, I'm trying to be a bit lazy. I did not do the window size check, okay? But in TCP sender, there's also a window size. So there should be an if condition here before creating packet to check whether the next seek num, okay, is still within the window limit, of course. And next, this is also a familiar transition. This is the transition when the sender receives an ACK. Well, similar to go backend's transition receiving an ACK, that's extract the sequence number from the ACK packet. Now, the action of TCP sender here is different. Only when the sequence number is larger than the send base, meaning this is a new ACK packet. So the sequence number here is something that has not yet been acknowledged. Then we send the send base to the new sequence number because now acknowledgement is received. Sender should say that that's slide the send base over. All right. Now, if there are currently not yet ACK packets around, then that's restart timer. So we'll be starting the timer for the new send base. If there are no outstanding packets, so if there are no not yet acknowledged packets around, then just simply stop the timer. Because this ACK here, acknowledges all the packets that are waiting to be acknowledged. Right? So, hey, looking very simple. That is also saying when y here equals the send base, we do what? Nothing. So if a duplicate ACK is received at the TCP sender, hey, timer does not get restarted, unlike in go backend. Yeah, even though the sequence number is the same, timer gets restarted, refreshed. Okay. And the third transition, again, very typical, this is the timeout transition. So when timer times out, retransmit the entire flight of packet from the send base, and then start timer. This is actually identical to go backend. Yeah, in go backend sender, there's actually one more transition, which is doing what? Checking whether the ACK is corrupted or whether the ACK is a NAC. Okay. In those cases, we do nothing. But you see, when ACK is received, do these. And when the ACK is new, is doing this. So all these other things do nothing. Is just, saying default actions all ignored. Okay, so from now on, if you don't see any other conditions being listed as a transition here, that means they will be just ignored. Now, this is just another way of writing the finite state machine, but in a pseudocode form. So we switch, different events. There's the data received from above case. There's the timeout case. There's also the receiving of an app packet case. So receiving data from app, generate packet, set the sequence number in byte count, and start timer if there's not one yet running. Just to make sure that you set the timeout interval to what? The estimated RTT plus 4 times the deviation of RTT. In timeout here, if it is triggered, then retransmit the whole flight of segments and restart timer. Receiving an ACK, extract ACK number. If the ACK number is new, meaning it's acknowledging something that has not yet been acknowledged previously, then update the send base. So we slide the window over. We restart the timer if there are still unACK packets waiting. Otherwise, stop timer. These are the only 3 events. If there are other events occurring not fitting any of these events, ignore. If you're not quite convinced, the previous slide is the pseudocode. This one should convince you. Okay, so what I'm listing here, typing up here, is essentially what the finite state machine is telling. Initialization, and this, it's gonna go forever. It's looping forever, just like every server here, right? Waiting for an event to occur and take the actions correspondingly. It's a switch essentially on the events, and there are 3 different events: getting data from above, timeout, and receiving an ACK. So, from a finite state machine, you can actually convert it to a pseudocode, give this to your programmers, then you get yourself a TCP sender implementation. Right? So, being able to write out from the thinking, from the designing of TCP sender to the finite state machine is essential because, that drawing the finite state machine out of your thinking process is simpler. Okay? Trying to write the pseudocode out of the thinking process, just too challenging. Okay? Once you get the finite state machine, then you can gradually transition that to pseudocode. And there, you are one step closer to getting an implementation of what you were thinking about, what you were designing about.
All right, so that was the finite state machine. Okay, not so bad, right? Very much like the go backend. How about let's go through 3 examples. And in some of these examples, you might see the benefit of doing the cumulative ACK in go backend.
As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data center here. Host B is just sending acknowledgements. Host A here sends 1 packet starting from sequence number 92. It's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay, so host A here waits until timer fires. And so the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. Right, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So yeah, the packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, we are trying to demonstrate the strengths of using cumulative ACK. That is here. If one of the back-to-back packets that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So to this point here, sender host A here seeing, ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back X, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short, so timeout occurs before X can come back. So first, timer occurred here. Therefore, timeout event in TCP senders trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Now, ACK 100, ACK 120 will arrive later. So when ACK 100 arrive at the sender here, Y equal 100, that is the sequence number in the ACK. The send base at this point is still 92. So Y is greater than send base. Therefore, we change the send base to the new ACK number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, hey, timeout occur, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here, we restart the timer, and this timer is associated with send base 100. When ACK 120 arrive here, we need to change the send base because it was previously 100, and the Y is 120, bigger than 100, so change the send base, slide the window over. Do we stop timer or restart timer? Well, there's no more outstanding packet because there are no more getting called from above. So, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver, receiver is going to see, data byte up to 99 received. But the thing is, the receiver has already received up to 119. So those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded. And an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when ACK 120 arrives at the sender, well, Y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the 3 transitions, we ignore it. Sender does nothing. The second packet here, with sequence number 100 will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, 100 to 119 bytes have already been passed up to the application layer. So another ACK, 120 is going to be sent back to the sender, and sender is just going to ignore it again.
All right, so that was 3 examples. But you know what? Some of you might be keen observing this. Okay, one of the states in the center-side finite state machine is actually saying send from the smallest segment. Okay, and you probably see also in the pseudocode, Polly keeps saying this is TCP sender simplified. You know what? TCP's RDT, the sender side, is a little bit diverted from the traditional go back in. Okay, and here's the video to explain where the differences are, and to give you the full, the complicated version of TCP sender.
And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay, the examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also, okay, explains in example 3. You'll see in the textbook, the authors will describe it this way. When send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back, in go back in, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. Okay? The description in the finite state machine says this: retransmit not yet act segment with smaller sequence number. Now we read on the actions being taken carefully. You see, this is not in the plural form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back in. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of condition control. Let's define more precisely what TCP sender does when there is a timeout event. Note that this is no longer the simplified TCP. This one is actually quite realistic considering condition control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting 1 segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way: 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, at the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round trip time plus 4 times the deviation of the round trip time. Okay. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh, wow. We were actually quite conservative here already, isn't it? That is what? Covering 99.99 something percent of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this. Yeah, window size dropping all the way to 1, and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more X coming back. That is probably because data cannot go out. But TCP being a pipelined reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of X, or maybe seeing some duplicate X, OX coming back. Not that we get no X at all and then eventually run into timeout. Okay, so timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down. Okay, by reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposing if this is go back in, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus a go back in. So we see similarity being what? Both of them are pipeline segment, and both use cumulative X, and there's only one retransmission timer, and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. In go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay, so exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously.
All right. Next is, hey, we just finished TCP's sender side and the complicated version. We have not yet talked about TCP's receiver side. In fact, TCP's receiver side differs also from go back in receiver in this. The ACKs are not necessarily triggered one packet per ACK. These ACKs can be delayed until the next one. Okay, so here's the detailed design, delayed ACK.
This is the delayed ACK. So this is the mechanism implemented at the TCP's receiver. Right? Now, in order to contrast TCP's receiver to go back in's receiver, let's bring back go back in receiver's finite state machine. And here it is, the go back in's receiver. There are only two events. First is getting a packet from the network layer, and it's not corrupted, and it's carrying the expected sequence number. Hey, this is the data packet we're expecting. So extract data out, pass it up to the application layer, generate the ACK packet, send back the ACK packet, and then increment the sequence number. So this is in fact the only significant event that we're expecting. All the rest, what the receiver of go back N does is just to send back the same ACK that has been generated previously. And back to TCP's receiver. So the first two events in TCP's receiver are these. Let's read through it a little bit. Arrival of in-order segment with the expected sequence number. Arrival of in-order segment with the expected sequence number. So both are events that's similar, right, to the significant event in go back N's receiver. Data arriving, not corrupted, and carrying the expected sequence number. So good news. we're supposed to generate ACK and send the ACK back. But at the TCP's receiver, okay, how we send the ACK back depends on the second condition here. So in event number 1, when all data up to the expected sequence number are already ACKed, okay, then we do one thing. If there's one other segment has ACK pending, meaning, hey, that segment there, we should be sending an ACK out, but it's actually pending. We haven't sent it out yet. Then we do this. Okay. Now, some of you might have guessed. Yes, TCP's receiver here is trying to do sending one ACK packet per 2 data packet received. So, if all data up to the expected sequence number have already ACKed, that's delay sending of this ACK. Okay. So that's wait for the next segment. When the next segment arrives, then we send the ACK. Otherwise, that's just wait for 500 milliseconds. When this 500 millisecond expires, yeah, we have no choice but to send the ACK for this data. So you see here, this is the other condition. When there is a back packet coming in and there is already one data packet that is supposed to be ACK, but the ACK is pending, which means it's waiting for the 500 millisecond. Then we immediately send one ACK, and this ACK here carries the sequence number of the later segment. Okay? And because the ACK is cumulative, so when that ACK comes back to the data center, it's going to clear both this packet and this packet. The third event is more like the default event. Okay? The similarity, however, is more the action being taken. Okay? So when we receive a segment coming in that is out of order, meaning it's carrying a sequence number that's higher than the expected sequence number, then we will buffer the packet. So as a result, we detect the gap. So let me illustrate so that it's a bit more clear. Okay. Previously, we have received multiple packets, okay, and they are arriving in order. But suddenly, we get a packet that is out of order. It's not quite what we're expecting here next. So there's a gap in the sequence number of the packets received. In that case, upon receiving such out of order segment, upon detecting a gap like this, we send duplicate ACK, the old ACK that has been generated before. This ACK here is then carrying the sequence number of the latest packets received in order. The last event is this. Okay. Related to the gap we might see in TCP's receiver. So if a segment comes in that partially or completely fills a gap, then we generate a new ACK. Okay. The sequence number in the ACK here will be still the latest packet arrived in order. Okay. So this will acknowledge all the packets before that.
All right. How do you like TCP's receiver? It's a little bit odd, isn't it? The transitioning the traditional go back in that says, oh, I receive a packet and it's expected, then I extract data, send back a new ACK. That in TCP's receiver is actually split into two, isn't it? One is checking if there's any packet pending acknowledgement. Okay. If not, delay. If yes, send a cumulative ACK. Okay, so the traditional go backend's receiver, that new ACK expand to 2 transitions. Okay, new ACK transition expands to 2. In traditional go backend's receiver, there's a whatever else, we just ignore the packet and send the duplicate ACK. That is for what? Out of order packet. In TCP's receiver, what do? We actually what? Buffer packet, and there's going to be a gap, okay, in the packets received. Okay, so this is definitely not the traditional go back in. And what's even more strange is the last event. That is what? In case we receive a packet that fills a gap. Okay, it's not only that it's expected in a way that it fills a gap, then you send an immediate cumulative ACK. And then you quickly slide what the new expected value is, expected packet value is until the next gap, right? So very strange. You know what? Quiz 24 is to write out the entire TCP receiver finite state machine. Okay, so that at least it's not just the go back end receiver, you see the entire TCP receiver finite state machine. And it's quite complicated as you see here, but let me go to the PowerPoint mode so that we can walk through individual transitions of TCP's receiver. So first is this one here. Okay, we receive a packet, it's not corrupted, and has the expected sequence number, right? This is the receiving new packets transition in the traditional go back end. Okay, but you see in TCP's receiver we have this two type of events that's for expected data that we are receiving. Oopsie, sorry. So actually I want there we go. Yeah, it's has the expected sequence number data packet. Okay, so next is we check, is it filling a gap? Okay, that's the odd strange transition. If it's not that odd strange transition and there's no packet pending for ACK, then we do what? We do, hey, here we wait for 500 milliseconds before sending this ACK. And when did we generate the ACK? We extract data, deliver data, and generate the ACK with the expected seek num, isn't it? And this is pretty much like traditional go back ends, a new data packet transition, except for this line, start timer. All right. And the other one, the counterpart, this is also receiving a data, not corrupted, has sequence number that is expected. Sorry that I missed the checksum here. But anyway, you know what I meant there. No, it's actually fine. You are checking the checksum here already. So it has sequence number that is expected. It's not filling the gap. And it's the situation where there is already an ACK pending, right? What do we do here? Yeah, of course, we extract data and we generate the ACK, which carries the sequence number of this guy, right? And we don't wait for 500 milliseconds. We just send this ACK, which is cumulative. This packet sequence number is going to be higher than the previous one that's pending. And here we also remove the timer that we have set previously, right? If pending is true, that means some data has been received and it's coming into a state, there's no packet pending, and a timer has been started. All right. So these two are actually necessary to split the traditional go back ends receiving new data packet, receiving the expected seek num packet transition. Okay, so that transition split into two, which is the T1 and T2 here. All right. Now, let's not check the traditional go back ends default, the everything else transition yet, because we still have this one, the fill gap, right? So these two transition, in some cases, we could be filling a gap. That is the odd transition in TCP's receiver. Yeah, so in case there, we are filling the gap. What do? Send a cumulative ACK immediately, and cumulative ACK is generated here. We send it immediately. And we just remove timer if there's one. Yeah. Okay. Because it's possible that there is a packet pending the acknowledgement. All right. Last transition. Yeah, this looks just like the other transition in the traditional go back end, isn't it? Default, send the duplicate ACK, set the pending to false, remove the timer. Okay, so this is TCP receiver's finite state machine. And quiz 24 is asking this, Q1, which transition is delaying ACKs and why? Okay, this one is the easiest and the most obvious. Second is, which transition sends duplicate ACKs and why? Okay, sorry that it's cutting out the why. Okay, Q2. Which transition might send duplicate ACKs and why? Q3. Which transition send new ACKs and why? Okay. Q2, somewhat straightforward. Q3, however, can be a little bit counterintuitive. All right. So that is Q24. We now go to the score, channel week 10, quiz 24. And for this one, I understand that it can be a little bit challenging. All right. So you'll be given 8 minutes of time to work on it. Okay. Now let's go. All right, so we can see that Team 7, Walker, has already typed up their solution. For Q1, it is very straightforward, right? Yeah, because only T1 is delaying the egg, starting a timer instead. So this is very straightforward. For Q2, T4 detects packet out of order. There's a gap, therefore send duplicate egg. Yeah, so this is for the case where, hey, the packet arriving is not the expected seek num. So send duplicate egg. So T4 is indeed the one sending the duplicate egg. Is T1 sending the duplicate egg? No, right? It is actually a packet coming with the right sequence number. T3 is also sending receiving packet that is expected. And it's sending an egg that is not duplicate. T1 is not sending egg, right? So you can probably also rule out the possibilities and come up with T4 being the one sending the duplicate egg. Now, Q3. T2 and T3 are the ones sending the new eggs. Obviously, this is new egg, T2. So let me come back here. Yeah, this is new egg, obviously. This is a new egg, obviously. T1 is not sending anything, of course, they're not sending new egg. The only remaining transition is T4. Is T4 sending new egg? Well, you know what? T4 was sending duplicate egg, right? Because when packet comes out of order, yeah, you simply send UDT send the same packet, which is an egg packet previously generated. But hey, guys, when will this egg be sent? Hey, sometimes it could happen that there's no more data packet coming in, right? When this timer has been started. So when is this expiring and when is this packet sent? Okay, and I see David asking questions. Okay, I'll come back to that question, but let's go back to Discord and see if we have alternative solutions for Q3. Oh, you know what? T1 for Q1. Yeah, so this is the transition not sending the new egg, it's delaying egg. T4, this is the transition sending the duplicate egg. But Q3, Team 12 says, not only T2 and T3 are sending new eggs, T4 also. Let's see what the reasons are. T4 sends new egg if timer expires, right? So the timeout event is actually not T1, T2, T3, therefore it's gonna trigger T4. And you know what? The send packet has already been generated here. So when timeout occurs, hey, the new egg generated here will be sent. So, wow, okay. You see that, yeah. Okay, I see Team 4. I'm sorry, Team 7 also updated the solution quickly. Great. It's a little bit tricky, isn't it? But guys, the point of this quiz is so that you are exercising, okay, how TCP receiver side works. okay, and make sure that the mechanism is very clear. All right. So go back in, there are two transitions. One is receiving packet that is expected. But now in TCP's receiver, that transition is split to three. One is, no gap, but no pending, so start the timer. The other, no gap, there's already pending, right? Send one delay ACK. And then, there's gap. Packet is still arriving with the expected sequence number, but there's a gap because TCP's receiver buffer packets. So that transition sending new ACK from the traditional go back ends receiver split now really into three. There are three different conditions. All of them are generating new ACK, but they are being sent at different timing and processed a little bit differently. Okay. TCP receiver actually tracks all these gaps. Okay, so there'll be buffering of the packets out of sequence at TCP's receiver. Unlike go back in, right? There's no buffering of packets if it's arriving out of order. Now the other transition, just everything else, send an ACK that has generated previously. Yeah, it is still the same, except that you need to change the pending status or removing the timer. All right, good. It's somewhat complicated, but if you think about it, yeah, sure, it works this way. All right, and you know what? Perfect timing to take a break. Guys, I think you're finally getting familiar with the TCP's receiver, finite state machine, okay? So for those who are still a little bit confused, take a closer look of TCP receiver's finite state machine. I know that you would see, it will work. And David, you know what? Let's take a break and I'll come back to address your question, okay, after the break. All right, so break time. right, so back to the lecture. I guess David's questions are answered. All right, and Walker was asking, why don't we just delay every act? Of course, we can do that, but what we'll be doing there is just delaying every act. Okay, the reason that TCP does delay act is to try to reduce the amount of act packets sent. Given that the act numbers are cumulative acts, right? If you send a later act, it acts everything before that. So you can exploit that property, the cumulative act, to send just, one act per 2 data packet, right? It saves you some traffic, saves you some bandwidth, right? So Walker, if you just delay every act, yeah, of course you can do that, but you'll be just delaying sending of the act for 500 milliseconds, definitely. Okay, that is not exactly better, and it doesn't save you bandwidth either. All right. Yeah, I hope that I addressed the question. Franklin, I have a question regarding 394 case 1 and 2. Suppose we receiver side send ACK and the sender send. Okay, so this is actually a few videos ago, and it's specific to a particular case and a particular side. It's a little bit hard to address this question, so maybe I can actually take this offline. And next is this TCP. We are almost done, okay, with the RDT, but not yet. The last video about TCP's RDT is just this: fast retransmission. It's an optimization, so the TCP doesn't need to wait too long to retransmit.
Last is the fast retransmission mechanism. In order to explain why we need fast retransmission, let's go back a little bit. When we were describing, when TCP sender experiences a timeout event, it's what? Dropping the window size down to 1 and setting the timeout interval to twice the current value. Okay? Because TCP sender, they actually consider a timeout event being network being congested. Now this is very reasonable when there is a congestion. TCP sender here, being a pipeline, RDT sends often segments back to back into the network, hitting the congestion point. Router there, buffer full, no more space. All these packets arriving back to back gets dropped. Receiver won't be sending any acts coming back. Sender has nothing to do but to what? Take the timer that started when we send the train of packets out. And so eventually, timer expires, timeout event triggered, and therefore we slow down very drastically. Okay. So congestion, and we slow the sender down drastically, makes sense. But what if the packets go out, did not hit congestion point, okay? And we just have a random loss packet in the middle of it? What does the receiver do there? Yeah, it's going to get packet in order, and then a random loss. All the subsequent packet arriving out of order are going to generate duplicate acts coming back to the sender. If you recall TCP sender, when there are duplicate acts, what do? We ignore. So sender there will still take the timer and have a timeout event eventually. And we are still what? Reducing the window size to 1 and set the timeout interval to twice the current value. That's overdoing it, isn't it? And that's why we have the fast retransmission mechanism. Because if we see multiple duplicate acts, and when there is a higher number of them, then you will probably guess there is a random drop right before the duplicate acts, okay? Or at the first unact segment. So that is exactly what TCP fast retransmission is doing. When sender receives multiple acts for the same data, to be more precise, it's triple duplicate acts. Then we resend the unact segment with the smallest sequence number, because this is very likely the lost packet there. Okay. So then we don't have the timeout interval being long problem, right? Because we'll be waiting a long time to retransmit just this sporadic loss. Okay? And this is to exploit the characteristic of TCP being also pipeline. We send back-to-back segments. In case of sporadic loss, non-persistent loss, we could observe number of duplicate acts coming back to the sender and resend the packet real quick without waiting for too long. And this example illustrates triple duplicate acts. Host A here is the data sender, host B here is the receiver. So window size warrants that we send 5 packets in one train. Let's say packet number 2, sequence number 100 is lost. Then this is going to generate ACK for sequence number 100. But this one is lost, so it's not going to generate anything. All these subsequent packets, it's going to just, trigger the receiver to send the same ACK back to back. So sender here receives the first ACK for 100. And this is the first duplicate ACK, second duplicate ACK, the third duplicate ACK. And this is when we begin retransmitting the first, the smallest sequence number that is an ACK. And so TCP sender's pseudocode needs to be modified. And the only part needs to be modified is this event, when we receive an ACK packet from below. Okay. First of all, we extract the sequence number in the ACK packet. And this is the case when the ACK packet is new. And this is the other case when the ACK packet is not new. So in here you see, we increment the count of duplicate ACKs. Okay. For each duplicate ACK, we increment this by 1. When the count for duplicate ACK is exactly 3, then we resend the segment. So this is fast retransmission of a lost packet. And then of course, drop the count back to 0. This is the last slide to summarize TCP's RDT. TCP's RDT is essentially go back in, so the base is go back in. But TCP being something that we actually need to implement and seeing running, defines very clearly the equation to derive timeout interval. TCP is also a little bit more performance conscious, so timer will only get refreshed when there is a new ACK. When there's a duplicate ACK, timer does not get refreshed anymore, unlike in go back in. TCP there is also not only doing reliable data transfer, it also does congestion control, flow control, and everything else. Therefore, we see when there's a timeout, the retransmission window is only dropped to 1, and the timeout interval could be doubled. More unique in TCP are these. TCP receiver here is also trying to reduce the effort of sending ACKs. TCP receiver here also tries to buffer that arrives out of order. So memory is required as well as the TCP receiver, unlike the go back in receiver. TCP implements also fast retransmission, so for certain patterns of loss, we get to recover faster instead of waiting always for a timeout.
Finally, TCP's RDT, finite state machine, is complete. So that was fast retransmission. If there are 3 duplicate ACKs, first new ACK, and then 3 more same ACK, then we quickly retransmit the packet that is indicated by the duplicate ACK that's missing. All right. There are just 2 more topics, flow management and connection management, we need to talk about. And these are related to RDT. Okay, so first is flow management. And this is actually also a little bit related to the next topic, congestion control. It's quite straightforward, and video is also rather short.
And that takes us to the flow control of TCP. Allow me to explain. Okay, so this is again the protocol stack. This is the application layer, transport layer, and the network layer. And packet is coming in from below like this. So network layer is going to pass the segment to the TCP receiver right here. If everything is okay, TCP receiver is going to extract data and pass it further up. What's going on really in the implementation in the operating system is this. That data does not go directly to the application layer process. There's this place here called the receiver buffer. So the packet being extracted is actually temporarily stored here, waiting for the application layer process to fetch it. So the application layer process is going to remove data from the receiver buffer. Just like the TCP receiver here is going to push more data into the receiver buffer. And TCP flow control is needed when the application is drawing data slower than TCP receiver there, delivering data up. Because when that is the case, the buffer space will be what? Occupied. More and more and more and more. because outgoing slow, incoming fast. And eventually the space is going to be exhausted. The subsequent data will be dropped right there between TCP receiver and the receiver buffer. And this is super bad because TCP here is working very hard to try to get this packet in. Okay. So full control there is this. For the receiver to tell the data sender, slow down a little bit so that you will not be overflowing the receiver buffer by transmitting too fast, too much. And the way flow control works is this. It works by tracking this variable, RWND. Okay. In the operating system, there's this receive buffer. This is well defined, and it's actually the size of the receive buffer space. Okay. Now, initially, RWND is going to equal the receiver buffer. Whenever TCP receiver sends data to the upper layer, this RWND is going to be subtracted by the amount of bytes being passed up here. Whenever the application layer process is drawing data out of the buffer, the RWND is going to be incremented by the number of bytes there. So RWND is essentially tracking this, the free buffer space. So once we manage to track the free buffer space, TCP receiver here will advertise the free buffer space by including RWND in the receive window field in the packet header, in the TCP packet header, and send it back to the sender. And that's when sender knows it needs to limit its sending window so that it's smaller than RWND. So you see here at the sender side, the sending window not only is limited by the congestion control mechanism, but also by flow control mechanisms, RWND. And that guarantees the receiver buffer not being overflowed. So receive buffer here, in most of operating systems, when you create a socket, it's set default to 4096. But most of the modern operating systems these days would actually give you different receive buffer space by default. If there's more space, then this is potentially higher.
Yeah, so now you see in TCP segment format, if you recall in the header, there's a field called RWND. Yeah, that field is used by the flow management mechanism. Okay, so when the sender receives an RWND that is actually below a certain threshold, the sender will try to slow down sending of new data. All right, so last one is called connection management. Okay, this is actually very important. It is to set the initial ACK and seek numbers for both ends. All right.
Last is the connection management of TCP. There are two parts. First is establishing connection. Second, breaking a connection. Let's talk about the process of establishing connection. It needs to be done before exchanging data, and the process is called a three-way handshake. Okay. At the end of the process of three-way handshake, we would establish a connection, or aka a socket. Okay. So once the socket is established, two ends can begin sending data to each other. So the socket establishment process is also exchanging some number of parameters. Now this is crucial because later on, when the client over here on the left is trying to send data, in the packet header there, it needs to carry a sequence number. When that packet arrives at the receiver, which is the server is going to examine the sequence number in the packet header to decide whether to extract the data out and pass it up to the application layer. And when do we extract the data? Only when the sequence number equals the expected sequence number. Okay. So there is a certain parameter at the receiving part, okay, that needs to be initialized. Okay. And because either side can be sending data, receiving data. So server here would also need to tell the client what is the initial sequence number server will be using. Therefore, the client can set the expected seek num accordingly. And this illustrates the three-way handshake. Client, server, both initially just listening, and client at some point wanting to request some data will then initiate connection, dial into the server. Okay. So it's gonna choose an initial sequence number to tell the receiving of the request messages. And it's gonna be sent in a TCP sync packet or sync message. Now, if you recall back in TCP packet format, in the header part of it, there are a number of these flags, one can set. So sync packet is the packet with the sync flag being set, the S flag being set. That is also called the sync bit. So that bit is going to be turned to 1, and the initial sequence number is going to be in the packet somewhere, and that packet is going to arrive at the receiver, which is the server. So client, after sending the data, is going to be in the sync packet already sent state. Now the server will then in the sync received state. So server here will be doing two things. First, send back an ACK, right, to tell the sender of the sync packet that the sync packet is received. So sync ACK is such a packet. That is to ACK receiving the sync packet. The server here will be doing yet another thing. Choosing its own initial sequence number, and let's say it's Y, and this Y will be stored somewhere in the sync ACK packet as well. So you see here, this packet goes back, and the sync ACK packet is going to have the sync bit on as well as the ACK bit on. And in sequence number, server tells the client it's going to start from Y. And this being an ACK packet is going to tell the sender of the sync packet that, hey, the next one I'm expecting is X plus 1. All right, so next seek num is already set to X plus 1. And lastly, when the client receives the sync ACK back, so it's going to receive the sync ACK. At this point, the client is sure that the connection is established. And so server is live. The last thing the client needs to do is just to acknowledge receiving the sync ACK. So it's just an ACK packet, and the ACK number is Y plus 1. Because this guy here observing the initial sequence number of the server is Y, then therefore the next seek num is set to Y plus 1. And that number is also shown in the ACK sequence number. And so server finally receiving the ACK is sure that the client is live and the socket is now complete and in the establishment state. The closing process is actually not exactly three-way. It's actually independent. The client can initiate the closing process. The server can also initiate the closing process. And the message exchange is just a pair of fin and ACK. So a fin packet out from the one who wants to close. And ACK will come back from the one receiving fin. Right? So there could be simultaneous fin exchange between the client and the server. So the client and the server are both exchanging data. And finally, the client here says, okay, I've finished sending all my data requests, so I'm ready to close. Then it's going to enter the no longer send but can receive data state. And that is called the send fin, and now wait for the rest of the data to come in. So you see here, the fin packet is the packet with the fin bit on. Server here receiving the fin packet sends back an ACK. So ACK bit on, and then ACKing the sequence number. Server here will enter the close wait. So server knows now that the client wants to close, but it's not quite yet closable because client setting close is just that finishing sending request. There could be some more data waiting to be sent here. Some more ACKs waiting to come back here. So server needs to finish all these other data that's remaining. But client here receiving the ACK for the fin. It's pretty much done, and just waiting for the server to say everything is already sent, so you're okay. So finally, server says, done with all the data. So sending fin. Client here is receiving the fin, sends back the ACK. Saying good, that's close. Server can now close safely, no problem. But client here needs to wait 2 maximum segment lifetime before it can really close. And this maximum segment lifetime is usually 60 seconds long. Can you guess why? Why the client needs to stay so long until it can really close the connection?
All right. Yeah. Guess what? And some of you might notice something that's really odd. When you're sending sync packet, the ACK for the sync packet, the ACK number is the sequence number of the sync packet plus 1. But you see that sync packet is not sending any data being 0 byte. But the ACK is sync sequence number plus 1. Same thing for the fin packet. Can you also guess why do you increment? Why does TCP increment sequence number for these control messages? ACK packet, fin packet. All right. Well, I'll leave these as, suspense for you to go and figure out. And we now will start the second major topic in chapter 3. So we just finished talking about RDT, the principle, and how the principle is used to implement TCP and how TCP also diverge from the principle. Similarly, we'll do the same for congestion control. We'll talk about what congestion is and what the general solution to handle congestion and how TCP handles congestion. So first video is just to introduce what is congestion, and it's in fact a review. We've already talked about it.
Principles of congestion control. Now the section title sounded a bit like we're going to talk about these general mechanisms to do congestion control. Well, but no, in 3.6, what we're going to talk about mainly are what's causing the congestions to occur. What is so bad about having these congestions? So hopefully from the discussion you see a little bit the nature of congestion and the design elements of doing congestion control. Congestion is this thing, having too many sources sending too much data too fast into the network. And by network here, I actually meant the core of the internet. Right? So congestion here sounds a little bit also like the problem we see in TCP, such that we need flow control. The situation there is that the TCP source sending too much data too fast into the receiver buffer. So the congestion there occurs at the receiver. And the resources that's being exhausted is the receiver's buffer space. Now when we're talking about network congestion, congestion is occurring here, routers. And these are the machines that are in the core of the internet. And the resources that we're exhausting there when congestion occurring are these, the buffer space. So router buffer is the resource that we're trying to handle. Now when we are all sending data into the core of the internet, you see that these buffer space can quickly be exhausted. If not, hey, we will have to wait a long time, or these packets will have to wait a long time, right, until they get served. So what's bad about having congestion is this. We see packet loss when the buffer overflows, or long delays when there are lots of packet waiting there to be served. Congestion there is one of the top problems in computer networks, just like reliable data transfer, and probably a little bit more serious than reliable data transfer these days. Coming ahead is a series of these scenarios, growingly more general, and hopefully by the end of the discussion, you see congestion is something that's really bad. You could invest a lot of time, a lot of resource, but you ended up having nothing.
All right, so from that side, can you feel that the relationship between RDT and congestion control? You can probably feel that they actually depend on each other. Because when there's congestion, you have packet loss, you have prolonged delay. And packet loss means what? The RDT needs to work harder, isn't it? Retransmit, sending more. Send packet two times, right? More use of the bandwidth. And when you use more of the bandwidth, the likelihood of congestion happening is also higher. Now you can probably understand a little bit that when we were talking about the complicated version of TCP's RDT, why there's some mechanism there to do congestion control as well. That is to control the window size, because the window size decides how much data can be out in one round trip time, isn't it? So they're actually intertwined. Okay, one depends on another. Okay, if one is well done here, the other also okay, need to work together with the other component. So yeah, interdependent. Now, to tell you a little bit more about the true nature of congestion, okay, I'll take you through three scenarios. They're actually very important. Okay, many of you guys in previous semester underestimated what these scenarios are suggesting. Okay, at the end you'll see the more work you do might not get you more results. Okay, usually when you spend more time on something, you get more results. But it's not necessarily true. When it goes beyond a tipping point, the more you do, the less you get. That's why sometimes you read these statements saying, hey, less is more. But less is less. How can less be more? What I meant by less, that quantity versus the more, the other quantity. Okay, these are two different quantities. Sometimes when you do less, the outcome can be more. The throughput can be more. All right? Three scenarios. First one, a little bit too idealistic, but straightforward. Let's start from there.
Scenario 1 is this. Okay, you see here, we have two senders, host A and host B, two receivers. Okay, so two servers receiving requests, I suppose. So two senders, two receivers. And we do have a link in the middle. The capacity is what? R. There's a router on the link and carries infinite amount of buffer space. Cool. So what that means is that there are no packet drops because it just takes a long time for the packet to go, but they're never dropped because we have infinite amount of buffers. Now let's assume that there's no bit error, therefore there's no need of retransmission because there's no packet drop and no bit error. Okay. Now let's use lambda here to denote the rate host A and host B are injecting data into the network. Okay, so host A and host B are actually raising the rate, okay, as time goes. Let's use lambda out to denote the amount of data that arrives at the receiver. Now, when lambda in is really low, starting from here, when we increase lambda in, yeah, the more data we send in here, yeah, the more data comes out here. Okay, so lambda out will actually increase accordingly. But this will only go up to here. Yeah, when we exceed the link capacity, because there are two flows and link capacity is R, so each flow gets only half of R at best. That means lambda out here can only, at best, being R divided by 2. So even though lambda in continues to send more, but no, we hit the limit, hit the ceiling here because resource is limited right here. Okay, we don't get to push more out. So increase sending rate, receiving rate accordingly. But here, even though we're increasing the sending rate, but the receiving rate remains the same. Now, the delay is going to show this way because when lambda in continue to increase, as you reach half of R, it reaches also the link capacity, right? Because this is also half of R, this is also half of R. And so at here, it's R completely occupied. So when we approach the link capacity, the queuing delay is what? Yeah, approaching infinity. So the first bad thing you see already, long delay when we send a lot more data and more than what the network can accommodate.
All right. So you see that, hey, we have a capacity. There's a limit in terms of all kinds of resources. For example, time is a resource. For example, network bandwidth is a resource, right? When the bandwidth is limited, the more you do, you don't necessarily get more. Okay. In this case, what you see is more not necessarily means more. Okay. More work not necessarily meant more result. Okay. It's not yet more. It's not yet less work give you more result. All right. Second scenario, let's relax, make it less ideal, and examine how come, right? When you do more work, sometimes you get less result.
And scenario 2 is actually very much like scenario 1. The only difference is this. The buffer space in the router there in the middle now has only finite amount of space. So in scenario 1, we have infinite buffer, so we don't have packet drops. Right? So what's bad about that scenario is just we will have long delay. But now in scenario 2, we have finite buffer space, so potentially we could have what? Packet drops. So potentially we need to retransmit packet. And retransmission here is at the TCP layer. So if lambda in is what the application layer processes generating the data to send out to the network, that lambda in prime denote the amount of data the transport layer needs to send into the network in order to complete the job. Okay? Then we'll see lambda in prime should be greater or equal to lambda in, because it should definitely contain the amount of data we need to send out, and plus potentially retransmissions of some of these data. Right? Lambda in, lambda out, the same thing. At the application layer, lambda in is going to be very much like lambda out. How much we send out, in the end, at the end of the time, lambda out is going to come out. And that was just to describe scenario 2. Now, let's assume the sender knows perfectly well when the router buffer is available. Okay, so sender sends data out only when there's buffer available here. So no packet drop. Okay, the scenario goes like this. At the transport layer, now we keep a copy of the data just in case we need to retransmit. But the packet will arrive at the router because there's free buffer space, so it travels through the network, reaching the destination. Okay, and echoes back, and we remove the copy. Right, so this is when the sender has perfect knowledge of the routers in the middle of the internet. Now in this case, there's no need of retransmission either, so lambda in prime is essentially the same as lambda in, and lambda in is essentially lambda out. So you see the same curve. We could have lambda in increasing, and we get the same lambda out up to the capacity of the link. To be more realistic, let's assume sender does not know whether the buffer space in the middle here is going to be free or full. Okay. So we'll have packet loss this case, because when the packet arrives at the full buffer, it's going to be dropped. And in that case, they will have to resend the packet. So packet arriving at the transport layer, at the sender side of transport layer, we keep a copy. Now, that packet arriving at the router sees buffer full, so drop the copy, and the sender there waits for some amount of time and retransmit. And this time, it happens to be free and it passed through. Receiver there receiving the packet sends back acknowledgement and removing the copy of packet here. And you see, at the application layer, there's only one packet being sent. But in the transport layer, we send 2 times the same copy. So lambda in prime, the output rate at the transport layer, it's definitely going to be higher than the output rate at the application layer. Now the output rate at the application layer for TCP is going to give you the same thing at the receiver end. Therefore, you see lambda in prime versus lambda out. It's going to be lambda in prime higher than lambda out. So in the end, even though the lambda in reaches its capacity, half of R, okay, but we don't get exactly half of R out here, because some of these half of R is going to be used for retransmission. So this margin here, unfortunately, is used for retransmission. So the actual amount of data coming out, less than half of R. And you see here, the bad thing, number 2, we have retransmissions when there is congestion here. To make it even more realistic, we know earlier when the buffer is full, the packet can be lost. The thing is that at the sender side, in order to detect if there's a buffer full, if there's a packet loss, we set up timer as well. Okay, so these timer can go out prematurely and therefore sending copies while we don't really need it. So it's illustrated by the animation here. Data coming from the application layer process, we keep a copy at the transport layer sender just in case we need to retransmit. Now let's assume that the buffer is free, but in case the timer is too short, we time out prematurely. We ended up sending 2 copies of data here, okay? While only one copy of it will be arriving at the application layer. So lambda out remain the same as lambda in, but we see here, the lambda in prime, this is going to be higher than the lambda in prime in the previous assumption, where we do not assume the timer can go out prematurely. So the performance of lambda out here as lambda in prime increases is going to go slightly worse. The margin here is going to be bigger because what? Lambda in prime here, we need to take into account the retransmissions. Now we also need to take into account the duplicates that are not really necessary. So we see delay being bad, retransmission being bad, and what's even worse is that we could have unnecessary retransmission. Now, if you think about it, congestion, we see that having packet loss, having delay, not good. But to address packet delay issue, to address packet loss issue, we need a retransmission mechanism, the RDTs. As a result, what? We are actually generating more traffic into a already congested network. So the cost, okay, of congestion is actually not that trivial. Okay? It's not just that the delay rises, it's not just the loss increases, but also the traffic being dumped, injected into the internet also increases. So in the end, the internet is doing even more work, while the throughput is not getting better and sometimes even worse. As you see, the margin here is bigger than the previous case.
Okay, all right. Hey, Polly, you said that, hey, sometimes less is more. But what we see so far in scenario 2 is that, well, more work, more output. It's just that the output is no longer proportional, okay, to the work you've invested. Okay, I don't know if you have experienced something like this before. For example, hey, if you spend twice amount of time studying, do you get twice amount of grades? Right? A lot of times not proportional. And you might also find that sometimes when you take more credits, more courses, you don't necessarily learn more. Okay, and sometimes you probably learn less. Okay, so the next scenario is the real scenario that's very similar to what's going on the internet, and you will see finally, less can be more.
If you think scenario 2 is bad already, where we do more work, right? Lambda in prime increasing, but lambda out increases at the beginning but saturates toward the end. Okay, so beyond certain point, the more work you do, you don't get more results. Okay? But here, I'm going to show you an example. Yeah, at the beginning, the more work you do, the more results we get. But in this scenario, the more work you do, you might end up having less results. And the even more work you do, the even less results. And here's the scenario. We do have 4 senders now, or 4 hosts, A, B, C, D. And each of them is generating a flow traveling multiple hops. So this is one hop. This is the second hop for the red flow. Okay. So multiple hops. And yeah, we might run into buffer full situation, therefore we could have packet drops, and therefore we do need a transport layer mechanism to try to do retransmission. So similarly, we have the lambda in, which is the input rate from the application layer, and lambda in prime being the input rate of traffic into the network from the transport layer. Okay. Now let's focus on the red flow coming from host A and the blue flow coming from host D. Okay. And these flows will increase the sending rate lambda in. And therefore, lambda in prime will also be increasing, and sometimes increasing faster than lambda in. Now, what's going to happen when lambda in and lambda in prime increases? Now, at the beginning, you see the red flow, the red packets coming into this router here. Okay? And as the rate increases, yeah, the buffer space here is going to be occupied by the red packet, just like the blue packet in the meantime, coming into the first hop router and occupying the front sections of the buffer space in the router there. Now, after a while, yeah, the red packet is going to come out and enter the second hop. Just like that, blue packet is going to come out and enter, yeah, this router here at the top. And the blue packet will be coming in to compete with the red packet that is already occupying most of the buffer space. Okay, so this is already pretty full when the blue packet just arrived. Okay. And as the lambda in increases as well, as they both approach a half of R, you see this. The buffer space is going to be very full and quickly. Yeah, red packet will be dropped, but blue packet what? Will be dropped even more because very few of these blue packets get into the queue and have a chance to go out, finally reaching B. So as lambda in prime increases, the arriving blue packets at the upper queue here, most of them get dropped, and therefore the throughput very small. So you see right there in scenario 3, the blue flow, right, when lambda in or lambda in prime is small, right, when the network is not saturated, when the buffer does not overflow, then the more work we do, yeah, the more output we get. But as it approaches half of R, yeah, we see blue flows, blue packets gets dropped a lot. So originally, not so bad, but in the end, when buffer flow could occur here, blue packet gets very little chance of coming through, and the throughput is going to be even lower, okay? Then when the lambda in here is small, okay? Really bad. So that is another cause of the congestion. Because what? The bandwidth that is transmitting these packets when they're traveling upstream, okay? It's all wasted. Okay? The amount of waste is actually not quite comparable to retransmission or unnecessary retransmission. Those are probably very small. Therefore, in the lambda in and lambda out plot we saw earlier, the margin is very small. But here, the upstream bandwidth, those are all wasted. Okay, so the amount of resources we are wasting here could be very high. Okay, so the hidden cost here, waste of all these upstream bandwidth resource, and this is a big cost. So
yeah, that's the third scenario and the time to get into the last quiz this week, quiz 25. Yeah, and with those scenarios, I guess it's quite clear to you that congestion is bad. Okay, longer wait time. You might have packet drop. You might have unnecessary retransmission, and you might have waste of the bandwidth you have used previously in the previous hops, right? So you might have experience before that you have a big job. Okay, and you've done the earlier part, but you get stuck in the last part because you are taking other courses, and then the time you need to handle all these courses, okay, is out of expectation. Therefore, for that big project, you had trouble finishing it. Okay, so that is the worst consequences of congestion. And congestion has troubled us in many aspects of our life. And quiz 25 is to illustrate yet another one. Okay, this is transportation. Okay, highway traffic. You see that every now and then Polly will use quiz to encourage you to associate. You know what? Congestion control on the internet doesn't need to be so different. Okay, the solution might be drawn from other systems handling their congestion. Okay, so maybe we can try to draw lessons from how transport system handles congestion. So this is a congestion in highway traffic. The scenario is that you are a Uber driver. Let's go to the PowerPoint slide mode. Yeah, so you are a Uber driver. And you serve mainly the downtown airport line. Okay, and you see already today, highway number 1, okay, from downtown to the airport, this route is badly congested, okay, as you drive your customer to the airport. Okay, Q1 asks, could you give us a few reasons why there's congestion on highway number 1? All right. Q2, based on your experience. Okay, and I know some of you might never get stuck in highway number 1. Then try to think of your other experience that you get, stuck in traffic somewhere. Q2, how do you inform your fellow Uber drivers so that they can avoid this route, right? As you see, congestion is so bad. And to get rid of the congestion, what do you do? Of course, make sure that the other drivers stop coming up to the highway, right? So so there are two issues. You notice there's congestion, right? First, how do you get this information now? And second, hey, we all need to go to the airport, right? How these Uber drivers, your fellow Uber drivers, can drive around, okay, highway number 1. Okay, so Q2 is actually asking how you solve the first problem. How do you spread the news that there's a congestion on highway number 1? Okay, so similarly, draw from your experience, draw from your observation of other drivers, okay, that try to do the same thing. All right, And let's go to the score space. It's channel 10, quiz 25. And you know what? It's already 12:05. Feel free to use the rest of the 5 minutes to work on this quiz. But generally speaking, this quiz is a take-home quiz. You're not expected to complete the quiz today. All right? So Polly will try to come back and grade quiz 25 on Saturday. All right, so that's all for today. Okay, starting next week, and by the way, you guys do want to attend next Tuesday's lecture because we will start talking about TCP, how TCP does congestion control. In one of the quiz 26, which is the next one, okay, it's a big quiz. Okay, it's a quiz. If you work really well, the whole team gets extra points. Okay, so every week I try to limit the score participation points to 5. For quiz 26, okay, it's a contest quiz. So you'll be pretending that you're contestants of a game show. Okay, if your team passed the first phase, all of the members get 5 extra points. Okay, and that's on top of the 5-point cap every week. Those who ended up winning the big prize every 10 minutes, that is the second phase, every team member gets 20 extra points for the score participation. Again, that is on top of the 5-point cap. All right. And you know what? Let me just add that channel and pose the question so you know a little bit what it is. Week 11, quiz 26. And so you get a sneak peek. 26. Let me make sure that it's the right quiz. It is. Okay. Okay, so this is a quiz that even though I tell you what we're going to do, you won't be able to prepare before this. Okay, so stage 1, you'll be asked, so you'll be guessing, okay, per team. Okay, not as an individual student. So each team will be asked to estimate the price of an item, and Polly will show that item, okay, in quiz when it's time for quiz 26. Okay, and the one that is closest to the true price, okay, and not exceeding the true price wins. And by the way, to make this somewhat random, Polly will take an item from popular e-commerce sites, shopping sites, and randomize the true price a little bit. All right. Stage 2. So those who win the stage 1, that team winning the stage 1 will win 5 extra points and enter stage 2. Okay. If that team wins the second stage 2, then that 5 extra points will be increased to 20 points. If you don't, you still get the 5 extra points. Okay, and that is for each team member. All right. So for stage 2, Polly will give you some hints when you are guessing the price. Okay, so that should make it a little bit easier. But hey, you need to guess the price right within a limited amount of time, 30 seconds. Okay, so it can be a little bit nervous, and it can be a little bit anxious, and for some students, they say it's exciting. All right, so that's all for this week, and I will see you next week. Okay, and I so look forward to quiz 26. Okay, that said, I say goodbye. Okay, goodbye, bye, and here's the goodbye music. Okay, bye. So that I can start the office hour.